So good afternoon everyone. Thanks for attending this conference. It's a very great privilege to be able to host Professor Roger Reid this afternoon for this conference. As Maggie said, this is the second conference we have in English. The first one was organized by someone also in this community of high temperature materials working at GE Additive and now Colibrium. And first of all, I'd like to introduce Professor Roger Reid. So Roger Reid did a PhD on steels at the University of Cambridge with Professor Badishia, who is very famous in that field. And then he has been appointed at Imperial College before moving to the University of Cambridge as an associate professor. And then he left for 4 years to the University of British Columbia in Vancouver, came back in UK as a professor, full professor in Cambridge again, then moved to Birmingham as a professor, and then to Oxford. And more importantly, he has been appointed as a fellow of the Royal Academy of Engineering in 2017. And since 2023, he is also the chief officer of the high temperature group, high temperature laboratory in the University of Birmingham. So it means that he has a joint appointment in between University of Oxford and University of Birmingham. And last but not least, recently Professor Roger Reid has been elected as the CNRS Fellow Ambassador attached to our group at ENSMA, so for the next 2.5 years. So it's a great honor, very few of them. If you look at the CNRS Fellow Ambassador, some of them have received a Nobel Prize, just to tell you the importance of such a prize. So it's a great privilege. As I'm always saying that Roger is one of the 5 gods on Earth on superalloys, with other colleagues from UK, one from France, and one from Japan, and one from the US. So it's a great honor to have him. And Roger, we are very pleased to have you provide this conference. So question can be English or French, and Roger is able to understand the question and also answer partly in French for sure. Thank you very much, Roger.
So it's a great pleasure to be here, and seeing so many young people makes me very jealous, because I used to be young once, and I'm not young anymore. I used to be the future, but the future is you. So hopefully I can try to inspire you a little bit about this field today. So thank you, Jonathan, for the very nice introduction, and I hope you can hear me. Actually, also, I was warned that the acoustics in your beautiful theatre is very good. So if you whisper at the back, apparently I can hear you down here. So please be very careful at the back, because maybe you say something which I can hear. Okay, so just some biographical details, and the main point I want to get across here actually is that we in the universities need to collaborate very strongly with the big companies in this field, because we don't make jet engines or space rockets and so forth. So having the collaboration with big companies such as Safran, Siemens and Rolls-Royce and so forth, and also the material suppliers you can see listed here, is very important. And so people like Professor Cormier and others are making giant efforts to work with those companies and to collaborate with them. Sometimes we also have to be a bit entrepreneurial, which means that we have to think about setting up our own company where there is space for doing this. I will try to say something about this. I set up about 10 years ago a company to do work specifically in the area of additive manufacturing, so what we call 3D printing. So I'll say something about this in my talk as well. So this slide here tries to inspire you to think about metallurgy or metallurgy, and really you can see here that it underpins nearly all aspects of commercial enterprise, energy production, conversion, and so forth. And so you can see here I make some claims about the fraction of all of the manufacturing inputs or values in Europe, it's a very significant amount of money. And of course, all of the people around the world want to or seek economic growth. And it seems to me that actually, of course, one of the big challenges is to find new kinds of metallic products that can allow this economic growth to occur, because we really want to have prosperity in the world. But yet we also have a problem because, of course, the production of metals contributes in many ways to global energy consumption. A lot of metals and minerals are being mined, which can, of course, lead to waste products. Of course, this is another a side of the story, which I don't really have time to talk about today, but it shouldn't be forgotten about when we talk about this field. The superalloys are really important materials, and you can see, courtesy of Professor Pollock here, gives a very nice example of materials which are used in really extreme environments for hypersonics or for very hot gas turbines or for generating power for blast resistance and so forth. We need to find materials which can work in these sort of very aggressive environments. And the superalloys are examples of these materials which have been developed by man and to humankind, to work well in these sorts of environments. The overarching questions in my career that have really motivated me concern, of course, the superalloys, which you can see are at the back of the engine here, at the very hottest part in the combustion chamber and beyond the back of the engine. And what we have to try to think about is designing alloys that can work well in those environments. I've also been quite concerned with trying to find good manufacturing processes to put these components into practice, particularly using numerical modeling. When I started my career 30 years ago, we had very, very small computers, and I remember having only about 1 megabyte of memory on my PC to do all of my work. And it was really difficult to kind of swap the memory in and out of what I had available. But I try to show you actually that it's been possible to model many of the manufacturing processes. And of course, what is also happening is that we're trying to find a way to integrate the materials aspects, the manufacturing and the design in this world. Okay, so this picture here shows you that the microstructure of these materials is pretty beautiful, but also the key point here I want to make is that the alloys here that we use are pretty complicated in themselves. From a chemistry point of view, we add 10 or more different elements, typically needing to specify the percentage here to very fine levels. And so actually you can see here that just from a simple thought experiment, it's not easy to optimize these materials from the point of view of trial and error. We need to have some kind of analysis method to optimize the materials. So I'm going to try to say something about that also in my lecture today. But I'm going to start by just telling you some of the things which actually, some of the manufacturing processes which are used for these sorts of materials. So I understand that not all of you are manufacturing engineers, but often we cast these materials into single crystal form, and this is done typically using a seed and a grain selector here and a helical selector. And then we have a ceramic mold which is withdrawn gradually from a furnace here. We have a dendritic structure which is grown, and typically also we need to heat treat the material after it's been cast. So these are examples of computer models designed by my group over many years actually, but specifically with the idea of trying to make a digital twin for this sort of process. Here's another example. We have turbine discs in the engine. Typically they are very heavy, maybe 100 kilograms in size. They're spinning around at maybe 10,000 revolutions per minute. Very big centrifugal stresses set up. we have to machine these parts in a very intricate way from large pieces of metal. And you can see here that the residual stress fields, which are typically inherited from the quenching operations, have a habit of redistributing as the material is machined away. So you can see here we were concerned with attempting to try to understand how that residual stress field is redistributed as the material is chipped away. And the reason why that's important is that those residual stress fields have to be accounted for in the lifing process for these components. They have to be taken account of in the estimate of the safe working life of the component. So precisely how we machine away the material becomes very important on the factory floor. Here's another example. These are compressor assemblies which contain the compressor blades, which allow the air to get squashed in the engine. And these are typically welded together. And of course, the action of the heat source, here it's an electron beam, as it passes around the disk, breaks the symmetry of the operation. So the stresses and the distortions which happen when we make that manufacturing process using electron beams has to be accounted for because we want to have the distortion captured. Here's another example. We want to try to find new ways of designing discs and blades because, of course, we want to minimize weight. Traditionally, the industry has made very widespread usage of these so-called dovetail joints where we mechanically fixture the blade into the disc. This, of course, requires us to optimize for the metal around the dovetail joint, which can be very heavy. So you can see here that there's a lot of metal at the hub of the disc, which, of course, contributes to the weight of the structure. So we try here to invent new kinds of friction processes involving rubbing together metal, making a friction joint, which allows us to build lightweight structures for these sorts of applications. Forging is also important in this field. So if you think about metal, we often want to form it into a particular shape. Here's an example of a preform for a compressor blade being made by pressing it into a die. Here, there is a risk of thermomechanical forces leading to cracking, and we want to anticipate in manufacturing whether this kind of thing can occur so that we can try very hard to avoid it. We often have sheet metal forming processes too. These can be very expensive in terms of not just money, but also in terms of the time scale associated with designing the dies. In this industry, typically you may have to wait between 6 months and 12 months for the delivery of a new die, which has to be very carefully machined. And we want to try to avoid many trial error iterations that get to a right first time philosophy for this kind of stamping operation. Okay, so I hope in the first part of my lecture there I've given you a flavor for the kind of materials and also the kind of manufacturing processes which are used in this kind of industry. I'm working most of the time at the University of Oxford, and in my laboratory at that university we emphasize 4 key pillars of research. We like to do advanced characterization. We try to design new alloys. We try to come up with novel methods for testing, particularly the mechanical performance of these materials. Very similar to the work which is going on in ENSMA, if I must say, at a much higher level and with greater impact. Then, of course, we're always interested in applications in this field. We want to try to find ways to make our research impactful. Here's one example. In my experience, it's really important to work closely with companies, but also to have good concepts. Here's a nice example of a collaboration we have had over many years with the Siemens company. The Siemens company is one of the biggest companies for making land-based turbine systems for power generation, typically generating, building machines generating maybe 50 megawatts of power. And typically in this field here, these single crystal materials tend to corrode very rapidly at high temperatures. So the temperature of the hot gas may be as high as maybe 1500 Kelvin, maybe even up to 2000 Kelvin in some advanced aero engines. And so there's a risk, of course, that the blades here will corrode over time. And so we had an idea here of trying to invent a new type of material that would have superior corrosion resistance. The idea actually was to try to come up with a kind of stainless steel version or stainless version of the superalloys. And the idea here was to have a chromium content equivalent to that of a stainless steel, greater than about maybe 12% by weight, so that we would have some very good corrosion resistance. And the concept here involved trying to balance the strength of the alloy, which is really strongly depending on the aluminium content, for reasons I'll explain in a few moments, against the corrosion resistance, which depends upon the chromium content. And in this field, you can see that the aerospace type alloys tend to be in this bubble over here, and the land-based turbine people were working primarily over here at much higher chromium contents to get their corrosion resistance, but at much lower strengths. So we decided to invent new kinds of alloys in this region up here, with the idea of having the strength of the aerospace alloys, but with much higher chromium content to give you good corrosion resistance. Now, one of the, this is a composition that we ended up designing here, but the key point of this analysis was to realize that the two phases which are really relevant to these materials, the gamma matrix and the gamma prime precipitating phase, have got different propensities for dissolving chromium. So by modifying the amount of the gamma prime forming phase, we were able to push up the net chromium content of the alloy towards higher levels. And in this particular case, it was this concept which is really important. And that's why I actually like collaborating with the French people. You have very strong concepts, very strong flair for design. And this is the key point that came from this particular research. And you can see here, taken from maybe 15 years ago, different trial compositions that we came up with on the computer with this idea of the digital twin, modifying the fraction of the phase and its compositions predicted by our thermodynamic databases. And you can also see here from so-called thermogravimetric oxidation tests that this new alloy, which had the code name STAL15, STAL stands for Siemens turbine alloy, has very good performance in oxidation. So under mass gain trials at temperature, you can see it has very low rate of mass gain because its oxidation reaction is very, very slow. Sometimes when we do these kind of projects, one of the beautiful things about science is that many, many things arise which we didn't really think were going to happen. So I can say with great confidence that we have been able to come up with really novel science too. These are microstructures of the deformation characteristics of this new alloy, which we found a very special kind of twinning mechanism here, which involved us needing to take needles of the material and then stripping off the ions one by one to identify atom probe maps here, which we could then interpret for evidence of this so-called micro-twinning here. I'll say more about this very neat technique later on in my presentation. Now, around about this time, when we were doing this work, we had the idea of trying to build large databases of conceptual chemistries of these materials and to relate each of those chemistries to the properties of the alloy. Bear in mind that conventionally, up until that point, people had been, by trial and error, so-called bucket chemistry, inventing new alloys, testing the properties and ranking them to see which was best. We decided we wanted to try to do better than this, and that process involved making many, many calculations on the computer and identifying these kind of ISO fronts here, which will allow us to optimize the composition of the alloy based on merit indices and design criteria to eliminate unsuitable compositions. This was a really nice thing which we did, I think, in retrospect, and we termed this method an alloys by design approach, because we wanted to be able to design alloys for their properties in just the same way, for example, that polymer chemists are able to design new kinds of polymer materials on the computer quite routinely. We patented this method. Actually, you can see here a patent that we put together to try to demonstrate that we had some intellectual property here to publish. Later on, actually, we also found ways to exploit this kind of technology for new kinds of powder disk materials. This is a very recent slide, actually, taken from the Rolls-Royce company. And you can see the kind of technologies, I won't read them all out, but you can see the kind of technologies that they believe to be important for a next generation ultrafan engine. And at the back here, you can see a new second generation high strength powdered metallurgy disc that was designed by my group, and again, patented, as these things have to be. And the key point here actually was to try to map the fraction of this gamma prime strengthening phase, and also this APB energy here, which we calculated using electronic structure calculation methods. It turns out that when you look at the theory here, you have these isobars, and we want to be working in the top right-hand corner of this material here, of this diagram. Existing available powder disk alloys, we believe, are somewhere on this contour plot, somewhere here. And of course, we were able to design new compositions to sit in this space slightly outside it. This was, again, the concept which was used for the alloy we designed. We published some information about this. The models were not completely perfect, but you can see here that when we compared the measured strength against that predicted by different kinds of computational methods, and not a bad correlation here. Not great, not perfect, but good enough to allow us to make estimates that were able to cut down the amount of experimentation needed. Okay, so round about this time in my career, about 10 years ago, I decided that we should try to apply this method to additive manufacturing. And the reason why I thought that was important is that history shows, if you look at this field, that every time a new process comes along, then usually we have to adapt the chemistry of the alloys for that new process. And people were trying very hard to use the existing materials, which are designed largely for investment casting or for cast and wrought processing, to this new method. And I thought to myself, no, this doesn't look right to me. We should try to design new kinds of alloys for this process. So we started to think about how to design alloys that would be amenable to 3D printing using laser-based methods. So for the next little bit of my talk, I'm going to try my very best to give you young people some advice, if you don't mind. I'm an old guy. I will soon finish my career, about things I have kind of learned about doing science. The first point, so you'll see kind of 10 points that will emerge. The first point I want to make is that as a scientist or as an engineer, be really curious about what is possible. We had this new process that was emerging, the 3D printing process. And of course, what it allows you to do is to really think about designing components in a radically different way. We don't have to machine away the material in quite the same way. So we can think about having thinner shells, manifolds. We can even have metamaterials like foams locally. We can have complex topologies inserted into our structures. So we have many, many extra design freedoms that emerge. We can let our imagination completely run riot. Here, excuse me. Yes, so for those of you who maybe are unaware about what additive manufacturing involves, we have a powder, and we spread this onto a base here. Then we use a laser beam to locally write the structure that we need to have in solid metal. Then we repeat that process over and over again. Typically, the thickness is about that of a human hair, maybe about 50 microns. And providing we have an accurate digital file that we start with, and we know where to place the laser beam, and we can make good decisions about that, we can build up these very complicated structures here by solidifying the metal locally using the laser beam. So that's what additive manufacturing actually is. And what this taught me is just think about what the possibilities are. While you're out walking or running or cycling, whatever you are doing, open your eyes and just think about what we could do with new sorts of structures. What this has taught me actually is that design is very, very important. So how we integrate structure, properties, modeling, and processing is very, very important. Now, I work most of the time actually at the University of Oxford, and we have some pretty clever students, but actually they're not really as clever as the people in France, I've discovered. I have this kind of thing in England about trying to ask people what they think they mean by design. And I usually start by asking, is the word design a verb? En français, un verbe? Oui? Comme ça? Oui? Or a noun? Now I show my ignorance of French. What is the French word for noun? It's the same thing, the même chose. Oui. Maybe I do know French after all. So is it a noun or a verb? And the answer actually is both. It's both. This is maybe the origin of the confusion, right? Because we have design indicating a concept, as in good design, functional, beautiful, so forth. What I think is the most important aspect, though, is actually doing design. And doing is un verb, en français. And so we can think about the action of doing verbs. But then we also have to think about design meaning a concept, meaning a kind of prototype. Sometimes we are using the word design to mean this. But then lastly, also, we can think about design meaning a final product, which has been designed, it's gone through the prototyping phase, and we have a final product that we can sell to the market. So we say design is to design a design to produce a design. And this is here really to make you think about what we know to be design. And of course, what you realize if you think about design is that good designs really are long-lasting. So for example, the concept of a canoe or a kayak, the basic design hasn't changed for thousands and thousands of years. The boomerang, again, a good design. This kind of coffee jug, you can still buy these sorts of things. They're nice. This basic structure is the same. And even the iPhone that I implore you to put away, basic design hasn't changed for about now, I think, would it be 25 years, something like this, or 20 years maybe? 20 years, which is an amazing thing. You know, you have in the world of consumer electronics, you know, a basic design that hasn't changed much. So think about being a good designer, knowledge of your market, designing your software tools. Think about human error. Well, is it human error or is it just bad design? I like to promote design thinking, and these books here are ones which have really influenced me in reading them. So I thoroughly recommend these. Okay, so a second concept for you to think about, I think finding ways to improve your observational capacity or your spatial resolution or the depth of field for your measurements. In my career, this has been very important. Here's some example. We think about how to test the material here by a test piece. Does this really have to conform to a standard? Or do we in a lab maybe want to try to change the design? Or do we want to maybe think about moving from a classical extensometer to a vision-based system? Maybe we need to measure the temperature not just with a thermocouple, but maybe also with an infrared camera. There's these days lots and lots of ways that we can find and store digital data about the way our materials behave. Here's one example. Don't be afraid to try to do things differently. Here we had the idea of building a brand new furnace with windows that would allow us to have access to the specimen, but from many, many different sides. Because some of these materials are deforming anisotropically, which means that they tend to move out of plane. And we wanted to have the idea of having a much better map of what the surface is doing. Here, the perspective ended up being very, very important. And you can see here that when we test the material from 4 different angles, or we measure the deformation, the perspective that we have here is very different depending on which camera we use, even though it's exactly the same test. So the perspective, what this teaches me anyway, is that the perspective depends very much upon your vantage point. And you can see from these sorts of measurements that we were able to map the surface strains as a function of the circumference of the material for different orientations of this particular material. And I credit Mr. Utada, who worked very nicely in Jonathan's lab for these very excellent measurements in Oxford. And you can see here that actually the stress-strain behavior in the limit here is very much dependent upon the camera here that we use. And this is due to the elastic and the plastic anisotropy of this material and its underlying deformation mechanisms. Here's another example fresh off of the press. I think these measurements were only made last week in my laboratory. You can see here that this is a stress-strain curve. This is actually a rectangular cross-section. And with the cameras-based systems, you can see the strain here. You can actually see the strain banding. I'll show it again. You can see here the strain banding occurring in this material over time. So the plastic deformation is clearly not isotropic. There are certain planes on which this material actually is deforming preferentially. So we're able now, I think, in this field to capture a lot more data. And how you young people deal with this data for calibrating and building new kinds of models with greater fidelity, I predict these things are going to be very important moving forward. Now, I said to you that we had placed emphasis on designing new kinds of materials for the additive manufacturing process. And here's some justification why this is important. If you look at this field, then in the 1950s, history tells you that we learned how to cast these materials in a vacuum. That was very important because they're very reactive, of course. So vacuum systems came along. We learned how to atomize the powder and then consolidate it. And then in the mid-1990s, additive manufacturing came along. Every time these new processes have come along, new kinds of alloy have been invented. So there's a kind of lesson here in life. I hope you don't mind me trying to impart some of my the feelings about this. What I have discovered in my life is that it's very critical to decide where and when to start a new piece of work. You can be late, you can be early, but getting it right in terms of its time is very important. We always need to be inspired or to be excited, to be creative. It could just be personal work, your own kind of way of doing things. It could be a pattern. You need to write a paper at the right kind of time. Even somewhere here, there are some students who have a big deadline on Friday. I met them this morning. Put your hand up. Yeah. You need to write your conclusion slide now, right? Don't leave it till Friday when you're in the bar. Trust me, do it now. Think about, what does success look like? Finishing your slide today and showing it to me before I go home, right? Please do it. How to get to the right destination. So here's one example. Very, very simple concept. If we think about the freezing range of these alloys, that's what this is here on the y-axis. This is some measure of the strengthening parameter that comes from the chemistry of the alloy. And I remember asking some students to plot on this simple graph here, where do all the alloys sit? Do the ones which have the hardest, do they have the widest freezing range or not? I didn't know the answer, but they did the calculations for me. And to my great astonishment, what I realized was that there was absolutely no correlation between the strength of the alloy and how wide the freezing range was. So we had a very, very simple concept. If we want to put these alloys into the additive manufacturing machine, where the cooling rate is perhaps 10 to the 5 per second, there's a big risk of cracking at that kind of speed, then we need to limit the freezing range and we need to limit the strength. And that was all we did. That was the basic concept here, to design alloys in this region here. And Professor Tang did this work for his PhD and postdoctor work. And you can see from these slides here, these are typical coupons for additive manufacturing material. This is the first generation alloy that we designed. And you can see here, right first time with these concepts, we were able to design something that actually performs better under identical tests than the existing alloys, which do crack under these circumstances. So this gave us great confidence in what we were doing with regard to designing new kinds of materials. We also have spent a lot of time collaborating with people. This hopefully will come across in my presentation. These are examples of atom probe maps where we are stripping away the atoms one by one and working out where they sit in the microstructure. I'll show you how we do this in a minute. But you can see here typical microstructures, predictions for the gamma-gamma prime equilibrium, and tests done of the oxidation resistance of these new alloys in this way. In Oxford, what we do with the atom probe, actually I should say, most of this technology was invented in France, in Rouen, with Professor Blavet. The Oxford people are just kind of copying what the French people discovered. But we make a tip here, and we make this very sharp, and then we strip away the ions one by one and pass them through a time-of-flight mass spectrometer to identify which species that ion corresponds to, whether it's chromium, nickel, aluminium, and so forth. Typically, what's done for the three-dimensional reconstruction is to have a counter electrode. We have also a gate here, a detector, and we measure the time of flight. And from the mass to charge ratio, we can work out which ion has been stripped away one by one. And these days, it's quite possible to build up maps of maybe 100 million atoms using this kind of technology. Here's an example of a typical spectrum that you derive in that way. And you can see that each peak here has to be indexed with software for determining which ion is which. We've been using this kind of technology for studying the reaction kinetics of the superalloys by the so-called time-temperature transformation diagrams. This is a work of Yuhan Zhuge in my lab, and he will present at the European Superalloys Conference these T2T diagrams here, where he's trying to understand the mechanism of transformation here for this reaction. And you can see here with the three-dimensional atom probe maps, he's able to show that the amplitude and wavelength associated with the decomposition reaction appears to be consistent with the spinodal type of phenomenon. Okay, next. This is a hollow structure. I think we should, as engineers, try to create structures of enduring beauty. We face really significant challenges in life. We had the idea of thinking about hollow structures. Why? Because, of course, for three-dimensional 3D printing, we are reducing the cost of the material. We can lightweight. We can add additional functionality. The basic concept here was to think about how we could remove one of the Achilles heels of metals. Metals typically tend to be very heavy with regard to their mass relative to water. Titanium has a density of about 4. Nickel alloy is typically about 8. We can make these ones lightweight here so that they can match the stiffness and the topology of bone. And this can be done using three-dimensional printing. Typically, these sorts of structures can be inserted into the humans. And the company that I set up has become an expert in doing these sorts of things. And you can see here, by using these sorts of ideas, new kinds of alloys for 3D printing structures that can go into the body has been happening. Typically, with these sorts of design scenarios, you have to trade off ductility against stiffness. You can see here the new alloy has a much less elastic modulus, but has good ductility. So for fatigue, it behaves really rather well. Okay, I think I'm running a bit out of time, so I'm going to just skip over these ones. A sixth lesson. Think about learning new language and terminology. This kind of thing is very important. I didn't really realize until later in life that we have to do this. New kinds of terminology. I remember being, in my younger days, the youngest person in the room. I'm no longer the youngest person in the room, usually the oldest. But when I was young, all of the old engineers would be busy using this terminology that I really struggled to understand. And it took me a lot of time to get the confidence to learn all of the language so that I could communicate and collaborate with those people. So some advice from me with regard to this. Number 7, and Professor Cormier is very good at this. Be really open about what you are doing. I believe very strongly in openness. This is the foundation of creating beauty, because when you are open, you communicate your ideas, then of course you are redistributing knowledge and information. So publishing is very important. So the question is, are you brave enough to be open? I hope so. It's important. New products inserted into the body, design products which endure. That's a typical component which goes into the heel bone for people who have smashed up their ankle by doing too much snowboarding in the Alps. So be careful. What we are doing currently in my lab is to try to get much better knowledge of the fatigue structure of these hollow type of structures. And this is, again, one area where I think we can do more and more. Number 9, go and see people, because you are going to be inspired by them. Go meet people. Go to see companies. Surround yourself with people who inspire you. What inspires you about people who are around you? It could be their product design, their courage. Maybe they're just very good technically. Maybe they have a really, really good story to tell. Maybe they are just brave. My tip in life is to work with the very best people you can. And if you do, you will be successful. And do it quickly, now. Write your conclusion slide. Because your life on the planet is short and you just never know what is happening. Last, work collaboratively. The material which I talked about in this lecture actually was made by the fantastic company Aubert Duval in Clermont-Ferrand, in Le Massif Central. Actually, I have to say, I was arrogant enough to think that actually we could try to do all the things for the powder in our lab. I was completely wrong. Completely wrong. Sometimes in life, I think you need to be aware of what your limitations are, because there probably are other people around who can help you with your work. So here we decided actually that we were much, much better off collaborating with the Aubert de Val company than we were trying to do things ourselves. Sometimes I think in life, and especially in business, you need to be brave enough to realize what your limitations are and to find people who can really work with you. And there's another example of the NTT data company so be entrepreneurial. These are the kind of things we are making with the new company, and it's been really nice to see actually that we have also recently made the press in the UK, in the Times of London. It's not the same as Figaro, is it, in France? And new kinds of micro engines for defense type applications. And even we are now in the top 100 tech growing companies in the UK, so this is nice. Okay, the very last slide. This might really surprise you, but every morning when I get up, I am a bit afraid about what I'm going to do at work. And I have found in my career that I have to confront my fears. Daily. I doubt myself. Can I do it? Is it right? Can I be enthusiastic enough? I have to go to work and I have to inspire my research group. And if I am miserable with them, with myself, am I going to be able to do this? It's a real challenge. So you have to think about letting go of fear. Somehow, I come to this beautiful lecture theatre and, it's amazing. But I still doubt myself. As I say here, I'm still afraid of failure and need to confront my fears daily. This is easy to say and do. My lesson, to have a chance of success, you have to let go of your fears and to try things. This is a valuable lesson. Many people helped me in my career. Some of them are here. And this is my summary. This is a fascinating field you're in. You're really lucky. Be curious. Increase your depth of field. Develop and have your ability to adapt. Don't stand still. Go and see people. This is really important. Be open. Publish your things. Work together, collaboratively. Start each day with optimism. Do not be miserable. No boss like me wants to have miserable people around. Professor Cormier, do you want to have miserable people around? Not at all. Not at all. Let go of fear. Be bold. And use materials to make structures of enduring ability and try to find new products. Merci beaucoup.
Thank you so much, Roger, because I have a new title. I think you guys might agree. I have a new title for your presentation, Life Lessons in Material Science. Pretty good, right? We were talking at lunch about I asked a question about the difficulty between where you find the balance between teaching and research, and your answer, I see it in the speech that you just gave. Your answer to me was, it's not a choice, it's not a decision. Everything, they're so related that it shows through, that my passion for my work shows through in my teaching. Absolutely, right? Absolutely. Super well done. So, what I thought, also thank you for pointing out to me a lesson that I learn all the time in working here, which is that we have the best and the brightest being taught by the best and the brightest. Truly, all of you are brilliant. I also want to end my part, and then we're going to move on to questions, just by one last little point, which is your last two slides. You said number 9, or the last couple. Number 9, you said inspiration all around you, right? Which there was a lot to be inspired by in what you just presented. So I want to thank you for being here, because by being here and by listening, you're giving yourself the opportunity to be inspired. And number 10, you said collaboration, which brings me to my giant thank you to Jonathan Cormier, who, without his collaboration with you and without our collaboration with each other, this whole thing would not be happening. So thank you very much, Jonathan. And thank you again, Roger. We're going to open it up for questions. Your turn. French or English?
So please raise your hand.
We'll bring a microphone to you.
Yeah.
Oh, you're sending me all the way up to the top? What? What is this?
First of all, thank you for this presentation. Is the advent of ceramic matrix composites in the aircraft engines rendering superalloys obsolete, as seen in the LEAP high pressure turbine shroud, or the rotating part of tests with GF 414? And is there any downside of using CMC instead of superalloys?
It's a very good question. I'm not totally sure I know the answer to it, but I know for sure that metal matrix composites have big potential and are already being used for certain niche applications in these engines. And I think you can imagine over coming years that they will be used increasingly. I'm a bit doubtful that they will completely take over from the case of the superalloys. But that's not based on a totally rigorous design analysis. I would have thought that if one looks at, for example, the specific properties of aluminium matrix composites or titanium matrix composites, then you can find ways to demonstrate that they should, of course, be used. I would have thought also there the question is one of reliability, whether we can be really sure that they behave over time as they should, and also whether their cost is justified in a domain of time when the engine manufacturers are looking for cheaper and cheaper products. That would be my view, but maybe Professor Cormier has a different opinion.
Maybe we can comment later on this, but they are used for static parts mostly. For rotating parts, I think there is a lack of strength intrinsically that will prevent them from being used for, let's say, all the stages of airfoils. And for disc, trust me, it will never be used. No capacity, no mechanical strength for this. Thanks for this good question. In fact, I would have asked this question myself. Is there other questions? Don't be shy.
Hello again. It's open. I want to ask. I want your opinion on superalloys. What else can we do for superalloys? Because as far as we learned till now, we are reaching the limits of superalloys with the chemical composition of them.
Yep.
What can be done for it to make it more better in this era?
I think the way I like to think of this question is to think about a turbine blade. If you think about a high-pressure turbine blade, typically it's coated with a ceramic thermal barrier coating. And actually, the thermal barrier coating is stuck onto the metal. The metal is resisting the loads in fatigue and in creep. And actually, we can't find a way to put the ceramic straight onto the metal. We have to find an intermetallic material to bond the two things together. In effect, it's like a glue. So here you have an example of perhaps a wall thickness of maybe 1 millimeter. You have a 100 micron thick intermetallic, and then you have maybe 150, 200 microns of ceramic. It's like, the British people and the French people and the German people all working collaboratively together in Europe, This is how it should be. I think the answer to answer your question, you need to find a way to get superalloys to work with other materials this is my answer to that question. Of course, we can always find new kinds of materials, but imagine, for example, that we had a ceramic for the turbine blade. It probably wouldn't last long. So just switching one material for another isn't really the answer. It's finding materials that can work together in a system, which gives the best performance.
Other questions?
Hello, thank you for your conference. I've got a question about the end of life of your superalloy. When you are designing this superalloy, are you taking into account the end of life, for example, recycling, reusability, for economic view or environmental view?
To be perfectly frank, the answer is no. We don't do that, and that's a terrible thing. I confess, if you think about, I think I had a slide in my presentation showing you the compositional complexity of some of these materials. We have up to 10, 12, perhaps even 15 different elements specified by Safran or Snecma or Rolls-Royce, and some of those elements are some of the rarest on the Earth, right? Rhenium and ruthenium and so forth. We have to find a much better way to consider these components from an overall life cycle perspective, because we know that these materials and minerals are critically endangered on our planet, right? Well, I think that's a really very good area, very good question, but a very good area for young people to get into.
Thank you very much.
Maybe I can add a further comment on this. The reality is that 95% of the superalloys are recycled. That's one of the easy kind of material, easy to recycle by melting. And just think about the production of the blades Roger mentioned. If you have 100 blades which are cast, maybe only 30 of them will be able to be in service in the engine. The remaining is remelted, as this is the easiest way to reuse the material. And this is expensive. That's the reality. Other questions?
Thanks for your presentation. You talked about alloys by design.
Yeah.
How accurate can you be in predicting the capabilities of such alloys? Like, how precise can it be in terms of like creep life or fatigue life?
Can you explain encore une fois plus lentement, s'il vous plaît?
How precise can designing alloys like numerically be, like in terms of creep life? Like,
Yeah,
how managing each?
It's a very good question. One way for me to try to explain this kind of thing is if we want to have a series of alloys, do we care precisely how accurate the prediction of the properties is? Of course we do. We would like to be completely precise. But there is also value in taking a list of alloys and ranking them in terms of their perceived importance. And sometimes, in my experience, the ranking can be just as important, at least in a preliminary prototyping stage, than the absolute prediction. Because, again, in my experience, in my life, all I can remember from 1990 or something is that people used to design turbine discs, for example, by choosing perhaps 10 or 12 or maybe 15 compositions. And a typical turbine disc, a prototype may cost you 100,000 euros. But you could only afford to do 15. And they was basically done with some people in the design office on an envelope and just writing some. This is how it was done. Crazy, right? So the idea to have some better computational approaches, maybe if they're not completely accurate, must be better than just trying and error. And of course, also what I learned in my career is that with regard to calculations and computer models, models are just approximations for the way in which nature behaves. And we have to accept an error. And of course, the philosophy should be to always drive down the error by improving the models more and more and more and more. You could then have a philosophical question, well, actually, is AI going to actually help us to improve the accuracy of our models? And, probably for some areas, yes, and maybe for others, no, but yeah.
The questions?
Thank you for the conference. I assure you that we'll finish the slide today.
Could email me to later.
You have talked about the gamma-gamma prime and the nickel-based superalloy. Are there serious alternatives to these ones, or are these really the only ones used nowadays?
Yeah, I think there were people, for example, in one of the most famous nickel-based alloys, you have Inkinos 718, you have a gamma double prime type of precipitate. So I think this could be one way in which you can improve further the properties of these materials. There's a lot of interest in, for example, oxide dispersion strengthened alloys again. So this is coming. Yeah. This is a man actually who is needing to write your final presentation for Friday, right? Okay, so here is one. This is completely off topic, but I'm going to give you my advice here. So I saw this team this morning, and they are telling me, well, we're in a rush because we have to finalize all of our results. And then on Friday, we're going to make our final summary of the conclusions of our project. And I looked at him. Comment t'appelles-tu? Why don't you make the summary slide now? Because this is what's going to be really important, and this is the one that the professor's always looking at first, right? And then all of your results have to justify the conclusions, right? So you can just write down all your results and then do your conclusions afterwards, or you could try to be different. Because you don't want to include every single one of your results in your presentation, right? Because some of them will be better than others. And the ones which are kind of loose around the edge, you think you're including them because you want to be impressive, because, you did so much work. It's just going to make your report confusing. So write down your conclusions and make sure your results justify the conclusions. This is my tip number 12 today. Bonne chance.
Any other questions in the room?
Thank you very much for the conference. It was really interesting. I wanted to come back to the simulations that you have shown us earlier, in which you represent how two pieces of metal are being soldered with each other by rubbing them against each other. And I wanted to know what physical models that you use in order to simulate this phenomenon.
Which one was the?
Yeah, on welding.
Oh, we used the software from Framatome for this calculation. It's this world. For the friction rod?
Yes.
We used for this one we used Abacus, and we also used the transversal software Forge 2, Forge 3.
So you use finite element method?
Finite element method, yes.
So you represent how heat is generated and how it's going to deform the metal?
So there is a friction law for generation of heat, and there is a sliding law. We had to think about the temperature, which we start to bond physically the metal. And the calculation is done in several stages, but you can read about it because we are open in Active Material, in a well-cited paper with 80 citations more. I will tell you which one to look at, published by one of my students, Mr. Turner. Yeah.
Thanks.
Other questions? So, last try. No further question? Okay, so if not, I'd like to thank you for attending this conference.
No, I want to thank you because this has been one of fantastic audience, fantastic lecture theatre, and really receptive audience, and you asked many very good questions, and I gave lectures in many parts of the world, and in France, what I really realized is that the French students and the young people are really receptive to science and engineering. So you should be really proud of what you are doing. It's fantastic. You have a really fantastic university here.
Merci beaucoup, Roger.
Vive la France.